All right. Section 6.6 is solving exponential and logarithmic equations. So exponential equations are equations in which variable expressions occur as exponents. So example 1, solve each equation. We have 81 raised to the x power is equal to 1/9 raised to the x plus 3 power. So now remember, what we're trying to do is we're trying to get some number that is the same, because once the number is the same on both sides, then what we should be able to do is just set the exponents equal to each other, and we've done that before. So if I look at here, I see 9. Well, I know that 81 is 9 squared, so I can go ahead and write 9 squared raised to the x power, and I know 1/9 is 9 to the negative first power, and that one will be raised to the x plus 3 power. All right, so now remember, what we have now is a power raised to a power, so that means I'm going to multiply them. All right, and even on this one here, I'm going to multiply them. I'm going to take -1 times x plus 3. And remember, so on this one here, I have 9 raised to the 2x power. If I distribute that negative through the parentheses, I'll get negative x minus 3. All right, so now, since the bases are the same and they're on opposite sides of the equal sign, I can state that the exponents are equal. So I can state then that 2x is equal to negative x minus 3. All right, I'm going to move the negative x over. So that'll give me 3x is equal to negative 3. And then that'll give me, if I divide by 3, x is equal to -1. Okay? Sometimes you're able to write them like that. Sometimes you're not. When you are not able to write each side of an exponential equation using the same base, you can try to solve the equation by taking the logarithm or the natural log of each side. Remember, yesterday we learned that the natural log, when we do a change of base, and the common log will do the same thing. All right? So on this one right here, I have 3 raised to the x power is equal to 8. Now, I don't really know what 8 is, but we know we have an exponent. And again, when I have an exponent up on top, it's easier to use logs. So since we have 3 raised to the x power, you're going to use whatever that base is. So we're going to use log of 3. So remember, that would give us a log. Remember, what I log on one side, whatever I do on one side of the equal sign, I have to do on the other side. We've done that so many times. So I put a log 3 in front of the 3x, and I'm going to put in a log 3 to the base 3, in front of the 8. All right? So remember, this right here looks like something we've seen before. Remember, the easiest way to think about it is that they cancel each other. All right? So the log 3 and the 3 cancel each other. So that means I can just bring the x down. And I can say that x is equal to log to the base 3 of 8. And log to the base 3 of 8, if you plug that into your calculator, you'll get 1.893. Okay, so now we're going to do some fun little a good application, So an important application is Newton's law of cooling. So Newton's law of cooling tells us that T is equal to T sub 0 minus T sub r times e raised to the negative RT, that is an R and a T there, plus t raised to the r power. Plus t sub r. Sorry, somebody kind of texted me right there. So where T sub 0 is the initial temperature, T sub r is the surrounding temperature, and R is the cooling rate of the substance. Okay? So example 2, and you'll have one like this on your homework, I know that for sure. Your sister is cooking her famous chili. When she takes it off the stove, its temperature is 212 degrees. The room temperature is 75 degrees Fahrenheit, and the cooling rate of the chili is R is equal to 0.051 or 51 thousandths. How long will it take to cool the chili to a serving temperature of 95 degrees? Okay, so let's go ahead and write the equation down here again. So I'll get T is equal to T sub 0 minus T sub r times E raised to the RT, okay, plus TR. All right. So if we write that out, our temperature that we want to serve it at is 95 degrees. Okay. Our original temperature or initial temperature is 212 degrees. Okay. And then the room temperature is 75 degrees. And then we'll have E. They tell us that our rate is negative 0.051. And our T sub r again was 75. Okay. So now, first thing we'll do is let's subtract 75. All right, when I do that, I'll get 20 is equal to, well, we can go ahead and do 212 minus 75 by ourselves. That'll equal 137. E to the negative 0.051. And I forgot to leave the T up there. T. All right. So now, again, we're going to kind of do what we did up there. So next thing I'm going to do is I'm going to divide by 137. All right. When I do that, I'll get 0.146 is equal to E raised to the 0.0051 T. All right. So now again, the T is an exponent up there again. So to bring it down, I have to kind of do what I just did up here when I did the logs. So how do I get rid of a E? Do you remember? Okay. Well, if you don't remember, you're going to take the natural log on both sides of both sides. Okay. When I do that, I'll again get the natural log of 0.146 is equal to the natural log of E negative raised to the 0.051 T. And remember, the natural log is log to the base E. So it does kind of look like this one here. We'd have log of E, right? So here we're going to say log of E, and there's our E. So by the same token here, we can go ahead and say that the E's cancel each other, so to speak. right? And I can bring that down, so I can say then I have negative 0.051 t on this side. And on this side, if I take the natural log of 0.146, I'll get 1.924. Make that 9 a little better. And then what I'm going to do is I'm going to divide by negative 0.0051, and that'll give us that our t is approximately 37.7 minutes. All right, you never really thought about cooling it off, did you? All right, so I continued here. Again, I should have put them together. That's why there's that nasty little line there. I think when I ran it through the copy machine, and I meant to take that off, but again, and I left you a lot of room so they could do work. So I'm not really continuing it. It's still the same. So those of you who took my notes, it should be on the next page. All right. So logarithmic equations are equations that involve logarithms of variable expressions. So example 3, solve each equation. So again, on this one right here, again, remember, logs are basically the inverses of exponents, right? So think the same thing here. If I have a natural log on both sides, then I can just say it's what is equal, they are equal to each other. On this one, I can do that, all right? So on this one here, I can say that 5x plus 2 is equal to x plus 10. Okay, so now I'm going to just solve it. So I'm going to subtract the x, so that'll give me 4x on this side. I'm going to subtract the 2, that'll give me 8 on this side, and then I'll get that x is equal to 2. All right, so again, let's go ahead and just get in the habit of checking some of these, and we'll see why here in a second. So check, I'll have the natural log of 5 times 2 plus 2. Again, our question when we're checking, does that equal the natural log of 2 plus 10? Well, 5 times 2 is 10, plus 2 is 12. So the natural log is of 12 on that side, the natural log of 12 on this side, it checks. All right, let's see on this one here now. Remember, when I have a log, you have to start thinking to yourself again, let's put it into exponential form. So think, this base raised to this power equals this. All right, because again, I have to kind of get rid of that log. So again, let's think, this base raised to this power equals this. So this base, 3, raised to the 4th power is equal to 10x minus 9. All right, 3 to the 4th power is 81 is equal to 10x minus 9. I'm going to add 9, so I'll get that 90 on this side is equal to 10x. And then I'm going to divide by 10, and I'll get that x is equal to 9. So, I did something to my wrist here. So, again, let's check, because it doesn't hurt to check, and it doesn't take that long, people. So, I'm going to take log to the base 3 of 10 times 9 minus 9. And our question then would be, does that equal 4? All right, so you would say log to the base 3 of 10 times 9 is 90 minus 9 is 81. And that will equal, does that equal 4? Well, yes. Because if you plug this in your calculator, you would get 4 equals 4. And it does check. Okay. Next one. This one here is kind of a long one, but again, it's a good one. So solve log to the base 6 of 6x plus log to the base 6 of x minus 1 equals 2. So remember, I have the plus there, right? So remember, what I can do is I can bring them together. That's what we learned yesterday. So I can say log to the base 6 of, let me go like this, 6x times x minus 1. That equals 2. All right, same thing I just did up above. This base raised to this power equals what's in there. All right, so now this time I'm going to keep the 6x times x minus 1 on the left-hand side. But again, I'm just kind of flipping it using the commutative property. So I can then state that 6x times x minus 1 is equal to 6 squared, right? So again, just to make sure you see it, this base raised to this power, so there's my base raised to that power, equals what's inside, which is what I have, okay? So now I'm going to distribute that 6x. So I'll get 6x squared minus 6x is equal to 36. Okay? Now remember, to solve for this, I'm going to set everything on one side, set it equal to 0. This is back from chapter 2. And remember, looks like I can factor out a 6. So if I factor out a 6, I'll have x squared minus x minus 6 is equal to 0. And then remember, since I have that, I can just go ahead and say that 6, because I'm going to divide both sides by 6. And what's 0 divided by 6? It's just 0. So then I can go ahead and say that equals 0. So now remember, let's see if you remember what I've told you. Okay, I have an x there, so I'm going to take an x and an x. I look at this one there. If it's negative, I know that one is positive and one is negative. And what are factors of 6 that will give me a negative x? All right, or a negative 1 if you want to think of it. So that would be minus 3 and plus 2. So then again, by the zero product property, we'll say that x is equal to negative 2 or x is equal to 3. Okay, so now, and this is why I gave us a lot of room here, because I need to write something here for you. So since, and let me use a different color. Since logarithms are undefined, for x is less than 0, x is equal to negative 2 is an, do you remember what the word is? Extraneous solution. So we have to check x is equal to 3. I mean, I don't have to check that one because it'll give us an error, all right, when it's less than 0. But it could work on other ones. So let's see here. So I'm going to say, then let's check. X is equal to 3. So I'm going to, again, plug it into my original equation, which is log to the base 6 of 6 times 3 plus log to the base 6 of 3 minus 1. Again, our question is, does that equal 2? All right. So if I do this one, I'll have log to the base 6 of 18 plus log to the base 6 of 2. Again, still our question, does that equal 2? All right. Then I'll take log to the base 6 of, well, 18 times 2, because I'm bringing them together. That would be 36. Does that equal 2? And again, you should be able to say yes. And again, just think about it this way, if you want to. Does this base raised to this power equal that? If that's the case, then yes, I can say then that this here becomes 2, or you can plug it into your calculator. Okay? So now, a little note here for you, just because I think you might have one or two of them on the homework. Remember, if it's not easily factorable, you can either use the graph, and remember, we learned how to find the zeros on the graph just by clicking it on the, at least on decimals, right? Or if it's still not, you can always use the quadratic formula. Okay, and again, notice I did give you a lot of room here, so that's why it's 3 pages. All right, and then finally, some properties work for equalities but are only true for when b is greater than 1. So same thing here, my x is up above, right? So if my x is up above, what are you supposed to do? You're supposed to take the log of both sides. So remember, I can take the log again. I'm going to take log to the base 2. I have to use the base that's the same as my base there. All right. And then I'm going to say, is that less than log to the base 2 of 36? And then again, like I just showed you before, those will go away. So then I'll have x is less than log to the base 2 of 36. And remember, this one here would be your exact solution. So if they ask you what the exact one is, you have to leave it in log form. If they say to round it to the nearest something, all right, you would then plug it in. And this one here, I used 5.170, and I plugged it in, and that would be your approximate solution. Okay, and let's do the next one here. Okay, so example 6, solve the common log of x is less than or equal to 4. So remember, the common log is like log to the base 10, right? So if it's like log to the base 10, you can tell me that 10 of log x, okay, and since I wrote it as an exponent, I have to write the other side as an exponent. All right, so I'll say 10 to the log x is it less than or equal to 10 to the fourth? So x is less than or equal to 10 to the fourth. Because again, just one more time, this was a definition earlier, so the 10 and the log 10 cancel each other. And then we'll have that 10 to the fourth is a 1 with 4 zeros. So remember on this one here, and let me again put it in a different color. So since logs, because remember it says it's less than or equal to, but remember log x is only defined when x is greater than 0. So remember, we have to restrict our solution. So we're going to say that x has to be between 0 and 10,000. And then finally, if you have exponents with variables on both sides of the equation, again, take the natural log or the logarithm or natural log of both sides. So we have 9 raised to the 3x power is equal to 4 times 4 raised to the 5x plus 2 power. Now remember, earlier we had these two numbers. These two numbers were the same. And that's why we were able to just use the thing. But since they're not the same, we could just use the exponents. But since they're not the same now, what you have to do is you're going to have to take the log or the natural log. All right? So since the bases aren't the same, so you are going to take the log or the natural log. Okay, so I'm going to take log the 9 of 3x is equal to log of 4 raised to the 5x plus 2 power. Okay, now remember, I want the x's down, so I can bring the x down to the front, remember, and the same here, I can bring it down to the front. So I can write this as 3x log of 9 is equal to 5x plus 2. And again, let's put parentheses around that because we know it all goes together. Log of 4. Okay? So on this side here, since we have 5x plus 2, I'm going to distribute that log through. So let me go ahead and state distribute. The right-hand side. So I'm going to say right-hand side. It might be the left-hand side sometime, but you never know. All right, and you'll see why this is going to work out for us. So if I do that, I'll have 3x log of 9 is equal to 5x log of 4 plus 2 log of 4. Okay, so now, just like any other thing, we're going to try to get the x's on the same side. So I'm going to have 3x log of 9 Remember, I'm going to take this one here now, and I'm going to move it over to the other side. So I'm going to say minus 5x log of 4. If you wanted to put it in the front and put the negative, it doesn't matter, okay, is equal to 2 log of 4, okay? So now, what you should be seeing here is, again, I have that x there, and I have an x here. So what can I factor out? Oh, you're right, I can factor out an x. When I factor out an x, I'll have 3 log 9 minus 5 log 4 is equal to 2 log 4. Okay, now to get x by itself, remember this is saying x times this whole thing right here. So if I divide both sides by that whole thing there, I'll get x by itself. So I'm going to divide by 3 log 9 minus 5 log 4. I'm going to divide this side by 3 log 9 minus 5 log 4. All right. So again, these ones will cancel each other. So I'll just have x on that side. And let's go ahead and just write it for you one more time. And remember, on this side here, so since it's all of it, and remember, sometimes your calculator wants you to have it perfect. So you should put the stuff underneath in parentheses, okay? Because if you don't, remember, your calculator is only as smart as the person putting in the data. A lot of times, if you just put 2 log 4 divided by log 3, 9 minus log 5, 4, it would look at and say, well, hey, he's just saying I'm taking this part right here. So again, it would take that out of the way, and it would say you're going to do that, and then it would subtract it, okay? But if you plug it in exactly like I have, show it to you, because remember, it's a common log there now, so everything is nice and usable. And if you plug that into your calculator, you'll get that x is approximately negative 8.1595. And see, it looked nasty, but it was pretty doable. All right. Thank you.